Welcome everybody to the next video in our series on computer programming for mathematics. I, as always, am Dr. Lathram, and today we will be continuing our introduction to the Python interpreter. So before we actually get to the Python interpreter and kind of playing around with the nuts and bolts of that, Python at its heart is an object-oriented programming language. And so it's probably a good idea to maybe have at least a little bit of an understanding of what that really means. And so I'm going to choose, being a mathematician, to kind of explain that or maybe give insight through an area of mathematics called category theory. And so the reference that we have here is Commutative Algebra with a View Towards Algebraic Geometry by David Eisenbud. It's an amazing reference. It's an amazing book. It is probably not light reading, but I encourage you to kind of pick it up and look at it, especially if you have a bent towards abstract algebra. And so in one of the appendices of that book, it has the definition of a category, and that's what I've listed partially from right here. And so it's not really a total definition of a category, but it will get the idea across as to what we're really talking about. So a category is basically a collection C of objects. And for each pair of objects that you have, you have a corresponding set of morphisms from the object A to the object B. Now, along with these morphisms, you have the notion of a composition law. So kind of in the background, what you're really thinking here is that you have some kind of functions on these particular objects, and those really are what you are calling your morphisms. Now, kind of common examples, so if you've had some experience with kind of mathematics, taking several mathematics classes, you may have been exposed to these already. I mean, kind of the first example, really just talking about sets with functions. And so if I have a collection of sets, then I can talk about functions from one set to another set. Those are really just going to be my morphisms. And so the category of sets with functions, or the collection of sets and functions, is a category. Another example, if I talk about groups, so groups being one of the first things that you encounter in abstract algebra, so groups together with group homomorphisms constitute another category. Rings, still kind of staying in the realm of abstract algebra, rings with ring homomorphisms are another example of a category. Topological spaces with continuous functions. That's now we've kind of left abstract algebra and gone over to a new area of mathematics, topology. So when we talk about topological spaces with continuous functions, that is an example of a category. And kind of the last one that we'll give here, not nearly an exhaustive list, but here's one of our last examples when we talk about vector spaces with linear transformations. So the objects that we're dealing with, and then what kinds of functions on those objects actually preserve the properties of the objects is kind of what we're dealing with. And so the functions that we have are allowed to operate on the objects themselves. Okay, so enter object-oriented programming, and we see that the idea is kind of similar to what we saw over in category theory. That instead of actually having objects and morphisms, we've got objects and methods instead of morphisms. And the idea is similar in that a method, we're really just thinking of it as being a function which can only be applied and really only makes sense when we're talking about a particular kind of object. If we're just talking about a group, then talking about the notion of continuity doesn't really make sense for some groups. And so we have to deal with the context of topological spaces. That's really the proper context in which to talk about continuity. And so the idea is similar here in that a method is going to be a function that's applied only to a particular kind of object. Now, I can define addition for integers and addition for rational numbers, but in doing that definition, as I'm kind of developing the rational numbers from the integers, this new operation of addition is really an extension of the addition that I had down in the integers. And part of what I do is then to say, I develop this notion of addition, and then I probably prove a theorem that says that the addition that I have here inside the rational numbers, when I look at the integers as a rational number, it gives something that's consistent. And so it's technically not the same thing, but it's an extension of the addition. The addition in the rational numbers is an extension of the addition that I had on the integers. It is not necessarily the same thing because it's being applied to a different object. And so the kind of the $5 term that we encounter in computer programming when we're dealing with those kind of things this is really the idea of a polymorphism. So we've taken something and we've extended, so it means this in one context and it means something else in a different context. In Python, how we denote that typically is with this dot notation. And so we'll become very, very familiar, and it will be second nature by the time we're done with the course. But the dot notation. So the dot notation is really just, we have our object, so whatever the object is, we have the dot, and then the morphism is actually the function that's actually being applied to the object that we have here. And to denote that it is a morphism, we have the set of parentheses that is applied to it. Now, something that also goes along with the dot notation is the idea of an attribute. So an object and an attribute, so kind of some piece of information that's really contained inside the object itself, is really what we mean by an attribute. Probably a similar example, if you are familiar with the C language, that this is an object is really just a structure. And a morphism is a function that can be applied on a particular structure. And an attribute is an element inside that structure that we have. So that's kind of another context of where this is similar to maybe something that you've seen in another programming environment. Now, kind of an example that we could do to maybe illustrate some of this a little better. Suppose that we are the owners of a company. Then we're programming for this company, then we can say that we have a class of objects that we will call employees. Then, if we have a particular person, so let's say that Bob works for the company, then we would say that Bob is an example. So Bob is an employee object for the company. So Bob becomes one of our objects. Bob may have certain information which constitute him as an employee. So he could have maybe an employee ID. He could have some hourly rate that he's being paid. He could have a particular department he's associated with. He could have the number of hours he's worked this year. And so that could be the pieces of information that make up Bob. Now, the employee ID, we might think of that as an example of an attribute that's related to Bob. It's a piece of information that's actually contained inside the structure of Bob. And so in Python, we might say that this is bob.employeeID or something like that. Again, this is kind of fairly loose. We've not really done any kind of syntax or anything like that, but this is mainly just to give you the idea of the kinds of things that we'll be dealing with. The function, so if we had a function that would take Bob and calculate his yearly salary, then the function that calculates his yearly salary would be a method that could be applied to Bob. And so kind of the syntax that we would be talking about there is bob.yearly_salary. And since it's a method, we have the parentheses being applied to it. Now, when it comes to actual variables, and variables are going to show up in our program, we can really think of variables kind of abstractly as just being pointers to a particular object. And we can change the direction of those pointers kind of with reassignment kind of any way that we want to. So some rules about variable names. So this is a good thing at this point to kind of get it out of the way. Rules and variable names. What are you allowed to do? What are you not allowed to do? So variable names, first of all, are case sensitive and may contain any letter, underscore, and any digits that you want to use. One condition is that the variable name cannot start with a digit. Otherwise, Python's going to think, oh, this is going to be some kind of number. Nope. So you have to start with either an underscore or letter. Now, there are certain keywords that are reserved in Python that has particular meaning for the interpreter. Those are off limits. So those are ones that you cannot use. So words like and. I can't use and as a variable name. Well, that kind of makes sense. I mean, that would probably possibly one of the dumbest variable names that anyone has ever considered. But anyway, you're not allowed to use and, assert, break, class, continue, def, del, elif, else, and so on and so on and so on. So any of these words on this list are not possible to be used as keyword, are not possible to use as variables. They are reserved keywords. And kind of the last thing, variables cannot be one of the built-in constants as true, false, or none. And so, again, why somebody would want to use true as a variable name, I really don't know. That would be kind of a strange thing to have to do. But anyway, just in case somebody tries, then true, false, and none are not allowed to be used as variable names. Now let's take a look at using the Python shell as a calculator. And so here I have idle pulled up, and as we can see that I'm using Python 3.5. And I am actually running this on Linux, so probably all the videos that you'll see from now on will be the Python running on Linux. It should look exactly the same, whether you got it installed under Windows or Linux or Mac. It should pretty much look the same, so we'll go with what I have on my operating system. And so the usual calculators, and so what we see here also as we're looking at it, these kind of three arrows there, they are representing the prompt. So every time that we get one of those, that's telling us that the Python shell is ready for to take an input. And so our usual notion for addition is really just the addition sign. So if we put in something like 2 plus 3 and hit enter, then Python's going to turn around and hand us 5. If we put in 3.1415 plus 2.67, then what happens? It turns around and hands us a decimal number. So addition works in the usual way with the usual symbol. Subtraction also works with the usual subtraction sign. So if I do 17 minus 9, that's going to turn around and hand me 8. No big deal there. Multiplication, 3.1 times, so I use the star for that. 3.1 times 4.2 is going to give me 13.02. Now notice that these are, in this case, floating point numbers. More about those floating point numbers later, but for now, we're just using it as a calculator, so we'll just kind of say, oh, those are going to be probably round off errors. Division will work as, so if I do something like 6 divided by 3, that's going to give me 2. If I do 16 divided by 8, that's also going to give me 2. So my division symbol works exactly the same way. Now, when I happen to be using integer division, so if I know that I'm going to be dividing integers, so notice that both of those examples gave me floating point numbers. If I wanted integer division, then I could do 16 two division symbols, and 2 division symbols divided by 8 is going to give me an integer of 2. But also, so the thing with integer division, if I would do 16 divided by 7, 16 integer division divided by 7, that's also going to turn around and give me 2. So it's not going to give me the floating point number. If I wanted the floating point number, I use the usual division, and so I get 2.85. Okay. The thing about integer division, it will kind of round it down. But then if I did something like, let's say that I want integer division with, say, -3 divided by 2, then I'm going to get -2. So it's really kind of going to give me the greatest integer less than the value that it would be as a floating point number. So if I did -3 divided by 2, of course I get the -1.5. The greatest integer less than that value is then going to give me my -2. If I wanted to do something like modular arithmetic, so if I wanted just the remainder when one integer is divided by another integer, let's see, how about we do something like 9 mod 2, so I use the percent sign for that. So 9 mod 2 is going to give me 1. So 9 divided by 2 is going to be 4 with remainder 1. And so the modular arithmetic is going to give me the remainder. Let's see, exponentiation. So we need to know how to do exponentiation. So if I wanted to do exponentiation, it's going to be represented as 2 asterisks, so 2 of the stars. So if I do 2 to the 3rd power, that's going to turn around and hand me 8. Okay, and so that's kind of the usual notation that we have going on there, just if we were doing these things with a calculator. And so I can combine these kind of in the usual way that we're used to doing in mathematics. So let's say that I wanted to do 2 times 3 raised to the 2nd power minus 4 plus 12. And if I do that, it's going to turn around and hand me 22 in kind of the usual way that I would think things should be evaluated. And so what we see in Python is exactly what we would evaluate on paper. Now, Python will not only handle our integers, our floating point types, it will also handle complex numbers. So we can represent complex numbers as something like, instead of using I being the square root of -1, Python will use J. And so if I had something like, if I wanted to represent the complex number 1 plus, so if that's the real part, and 1 plus 1j, Python is going to recognize that as being a complex number. If I took something like what I might think of as just being I, 1 times j, or 1j, and if I multiply that, so what happens if I take that number and I raise it to the 2nd power? Okay, what happens when I put that in? It turns around and hands me a -1 plus 0j. So that does say that yes, this is going to be the same thing as the square root of -1 in that case. And now kind of, since we've talked about a little bit before about methods and attributes of numbers, here's kind of our first example of where that's going to be used. So if I have, so let's say that I have, let's assign it to a variable, say 4 plus 8j. Okay, now you might wonder, well, what happens if I have to actually put a multiplication sign in there? Well, let's see what happens when we do that. If I do something like 2 times j, then Python will tell me that, oh, wait a minute, j all by itself is not defined. If I want to refer to j, it has to be some floating point number or some integer right in front of j. And so Python's not going to recognize a multiplication times that. It's going to return you an error in that case. And so for my value x, it's going to be the complex number 4 plus 8j. Of course, that thing has a real part and an imaginary part. Well, I can access those parts. They are attributes, so they're characteristic of this object, this complex number x, and I can access those with using the dot notation. So my variable x, and here it's idle, is prompting me with what values can I put in there? Well, I can put in the real part. So if I put in the real part of that, it's going to turn around and hand me 4. If I do the imaginary part of that, it's going to return me 8. And of course, now a method that I can use to apply this, so a function that I can apply to complex numbers, is to take the complex conjugate of them. And so if I would do x dot conjugate, and now because that's a method, I'll put the parentheses around there to say that this is going to be a function that's going to be applied to my object x. If I do that, turn around, and it's going to hand me 4 minus 8j. So it's going to take the complex conjugate of my complex number. So there's probably our first example of attributes. So the real part, the imaginary part, are attributes of the complex number, and then the first method that we see applied is the conjugate, so taking the complex conjugate of our complex number. So kind of a couple of the built-in functions that we have, so a couple of built-in methods that we can apply to kind of any number that we got, an integer or floating point number, complex number, actually for that as well, is the absolute value, and that's represented by ABS. And so if I did help ABS, it will return you. So this is kind of a nice thing to have also in the idle shell, is that I can just type help, and whatever the object is, the attribute, or the method might be. So if I do help abs, then it's going to turn around and tell me that it's going to return the absolute value of the argument, and that's going to be dependent on what I'm actually handing it. You say, now wait a minute, what happens there? Well, yes, just like in mathematics, we use the absolute value bar, so the two vertical bars to represent absolute value. Well, when you go to complex analysis, you use those absolute value bars as the absolute value of a complex number. And so the modulus of the complex number, so how large that complex number actually is. Now that's a different thing in the realm of complex numbers than it is in the realm of real numbers. So here, the formal kind of programming way of saying that, at least in Python, is that this is an example of polymorphism. And so we're kind of using the same function, but we're using this function applied to kind of two different types of objects, but it's really the same function. Mathematics, we do that all the time. We're kind of used to doing that, absolute value being the primary example. Operator overloading is kind of another way of saying that. But just anytime that you hear the word polymorphism, think absolute value, because the absolute value of a real number is going to be a different kind of thing than the absolute value of a complex number, even though we use the same symbol to denote it. And so if I would do the absolute value of 4.1, of course, it's just going to hand me 4.1. If I do the, absolute value of negative 4.1, it's going to hand me 4.1. And if I would do the absolute value of 1 plus j as my complex number, it's going to return me something that really looks like the square root of 2. And so there I have this example of I'm using the same thing, but for real numbers, it's computing it one way. For complex numbers, it's computing it a different way. That's the fancy schmancy term again, is polymorphism. And so kind of what we just saw was that number, we just computed the absolute value of 1 plus j, or 1 plus I, as a complex number. And gave us something that looked like the square root of 2. Well, what if we wanted to calculate the square root of 2, or if we wanted to have something like that show up? Well, how do we use that? Because if I just type square root, Python has no idea what that is, and so we need to figure that out. Well, now's our first example of using a module. So we're going to import code that actually tells Python what functions that we're using. And the command to do that is, since these are all mathematical functions, we import the math module. And so what that does now is give us access to a whole bunch of mathematical functions that we didn't necessarily have before. And the way that we do that is with the dot notation. And so if I want to take the square root of a number, then if I did math.sqrt for square root, well, what about math.square root of 2? Then sure enough, yes, I see that back up here, this is going to be my 1.4142, and I get the same value as I had up there. And so the math module imports lots of common functions that I would use. If I do the exponential function, so the e to the x, so that would be represented as math dot exp of whatever. So if I just do e to the first power, there's my 2.71828. And so that gives me my exponential function is my e to the x. Logarithms. Now, Python, if I want to do the natural log is denoted as log. Okay, so I might be used to looking at that as log base 10, but if I don't give it a base, it will assume that it is taking natural log. So if I do the natural log of 2, then that's going to be my natural log of 2. But as you can see there, it could prompt me that if I wanted to give it a different base. What about math.log of 2 to the base 2? Well, that's going to return me 1, of course. If I wanted base 10, then I could represent that as math log whatever it is, 3 base 10. I could do it that way. Or if I only want base 10, I could do log 10 of 3, and that would give me my usual base 10 log that I'm used to seeing there. And so, of course, I've got my sine, cosine, and tangent. So math.sine of, how about math.pi over 2? It's going to give me 1. If I do math.cosine of math.pi over 2, I guess I kind of jumped the gun there. I've got a constant, the usual constants you would think, pi. So math.pi over 2. I don't quite get 0. Again, that's kind of round off error. Okay, more on floating point numbers later, but here's an example. that floating point numbers in computer land are not the same thing as the floating point numbers that we see in our usual realm of mathematics. Okay, and so, but if we kind of wanted to go through and see what other functions are available in the math library, then if we just type math, then wait a second, math period, then idle will tell us kind of what's available. We've got arc cosine, arc hyperbolic cosine, arc sine, arc hyperbolic sine, arc tangent, the ceiling function, the cosine function, degrees, the error function, the floor function, the factorial function. So if I wanted maybe the factorial function, factorial of, how about 4? So 4 times 3 is 12, times 2 is 24, and so the factorial function returns me 24. So if I do the factorial function, how about if I did the factorial function of 12? The factorial function of, how about 60? That gets a really big number, so the factorial function of 60 factorial is huge. And this kind of brings up another aspect of Python as a calculator, in that it has arbitrarily long representation of integers. And so for that, we can really have as big of integer as we possibly want. Again, the Python interpreter is going to handle the memory for that. It's not something that we need to worry about, but that's kind of a nice aspect to have sometimes, to know that our integers, we don't worry about how big they need to be. Not necessarily true for floating point numbers. Again, floating point numbers are a totally different beast in and of themselves, but kind of a nice aspect to have when we're dealing with integers. So this has kind of been an introduction to using Python, using the Python shell as a calculator. Hope you've enjoyed it, and I would encourage you now to go and fire up your own shell and play around with it, import the math function, play around with some of those, try different things, see how they work, and just enjoy it and have fun. So I hope you enjoyed this video, and we will see you guys next time.